Okay, Assalamualaikum warahmatullahi wabarakatuh. So in this video, I would like to explain how to analyze indeterminate trust. Okay, this is internally indeterminate trust. Okay, this is the question. This as in the screen right now. Okay, the question is this trust is internally indeterminate trust. Internally indeterminate trust means the redundant come from member. Member force is the redundant, not reaction. Okay, so using the flexibility method, calculate force in member BD. Calculate force in member BD. Axial rigidity for the truss is constant. Okay, this is the basic question. Actually, force in member BD as stated in the question is actually the redundant. And by looking at this truss, okay, at this truss, we can see that there are three unknown reaction which come from support. Okay, let's see the solution. Okay, let's see the solution. Okay, we can analyze redundant in truss using flexibility method. To do that, we need to identify whether the redundant in the truss is come from reaction or member force. So this is the special about truss where redundant may come from either reaction or member force or combination. But this is the example of one redundant system. Okay, please take note that the truss must be stable and determinate. Always remember that whenever we remove redundant, the structure must be stable and must be determinate. Okay, so we have to remain the stable structure must remain one pin one roller. The stable structure must remain one pin one roller. So by using formula. So the formula to calculate DOI for truss is M plus R minus 2J. And we calculate the value and we get the value is equivalent to 1. The value is equivalent to 1. Anyway, we cannot simply choose reaction as redundant because we have to check the stability. Okay, to check the stability. So remember that the minimum reaction which come from support must be 3. Okay, it must come from one pin, one roller. So means that so for the stability, so this is equal to 0. So means that the reaction we cannot remove reaction which come from support. We have to remain reaction. We have to remain support. We cannot remove reaction redundant come from support. So what we need to do is, due to this, when we check for the stability, so we must remain the roller support and the pin support in the system to get determinate and stable truss. So we have to choose force a member force as redundant. Member force as redundant. So due to this condition, redundant in this truss come from member force. Redundant in the truss come from member force. So basically, when we have truss like this, okay, we can remove either member AB F sorry AC this one, or we can also remove member BD, either one. So we have two option. We have two option. Either we want to remove FAC, or FAC, or we can also choose FBD. And okay, for this example, I have actually choose to remove member BD. I chose to remove member BD, means that my redundant is FBD. So from the redundant that we have chosen, we write the compatibility equation. We write the compatibility equation which come from the principle of superposition. Okay, the principle of superposition. So what we get? What we get as usual, as done in frame, in beam as well. So once we have decided the redundant, so what we have to just to follow the standard form of compatibility equation. Since FBD is force, so we will determine displacement. It is delta 1 knot plus F11 times redundant, and we put the name of the redundant in the equation. And this is the compatibility equation. So what is delta 1 naught? Delta 1 naught is displacement in the primary thrust, and F11 is displacement in redundant thrust. So these two displacement will be determined by adopting, okay, deflection formula that we have learned. You have actually learned about unit load method, because unit load method is a method to calculate displacement. So we adopt that formula and we amend to suit with the flexibility method. So what we should calculate is basically okay. Two displacement, we have delta 1 naught and F11. Both displacement come from two determinate system. Okay, so we have delta 1 naught. Delta 1 naught, always remember that the label, the notation that we use is very, very important. So when we have 1 naught, means that it is N1 times M naught. N1 times N naught. Okay, N1 times N naught. And for F11, we will calculate N1 square. N1 times N1 is N1 square times L. So we get this from original formula to calculate displacement, which is summation. Okay, have summation here. Need to put summation, so I forgot to put this summation inside, in front of the formula. It is summation n times L over A E. N times L over A E. N times L over A E. Okay. So what is N naught? N naught is the member force. N naught is the member force for primary thrust, because naught is always labeled for primary system, and N1 is the member force in redundant number one. Okay, so what we need to do after this, we have to analyze two system. Number one is called as primary thrust. Number two, okay, we will analyze redundant FBD applied. Okay. Okay, so the member forces in the primary thrust, okay, are calculated using method of joint. Actually, we analyze using method of joint, but we do it virtually. Okay, method of joint that we do it virtually is called as easy method. Easy method is not the specific, name. It is just the name that we put, okay, in order to represent the process, okay, that we do it uh, in easy way. So it is actually method of join. We do it virtually. Because most important is not the method but the value, the member force itself. Okay, so we do it virtually by maintaining the equilibrium condition. So how to do it? We have to maintain external equilibrium as well as internal equilibrium in the system. External equilibrium means if there are external forces, so we have to balance with the reaction at the support. Okay, and then internal system also we have to we have to remain equilibrium by uh, by using by maintain joint equilibrium. Okay, we have to maintain joint equilibrium, means at each joint we have to make sure that it is balanced at each joint, balance in X direction, balance in Y direction. Okay, note that the reaction in the primary thrust is not compulsory to calculate. Reaction is not compulsory to calculate, because using easy method, virtual method of joint, we do it virtually, we call it as easy method. So using easy method, we can actually determine the member force without calculating without calculating reaction in the first place. Okay, without calculating reaction in the first place, and at the end of the process, we will get the reaction. Okay, but what most important is member force, because we want the member forces to include into the table. Okay, so reaction will be getting later to balance each joint. Okay, the member forces in primary truss is shown in this figure. Okay, so this is actually the member force that we calculate using easy method. Using easy method, so we can check. We can, okay, actually, okay, I forgot to put another one value here. This is 142.86. Okay, so actually I start from B. Okay, I start from B because at B, okay, if this is 250, it must be balanced with 250. Okay, and there is no horizontal force, so this one zero, this one also zero. That is why we get this as zero. Okay, and we get this as 250. The direction is opposite. The direction here is opposite. Okay, so this one. So after this, we move to C. We can move to C. So if this is 100, sorry, if this is zero, and we have okay, C we have 200, must be balanced with negative 200. So where is the negative 200? This one. Okay, means that the inclined member AC, we have to resolve in X and Y. So the X value will be 200, okay, in left direction, so that balance this. Okay, balance this. And after that, we have to interpolate to determine 142.86. We have to interpolate to determine 142.86. So in interpolation of this, we actually use trigonometry. This is 7, this is 5, so this is 8.6. So what we do is we interpolate, means that 7 is equivalent to 200, so 5 is equivalent to what? Okay, so this one, when we interpolate means 5 divided by 7 times 200. So this is equal to 142.86. So this is called as interpolation. This is called as interpolation. Okay, so we get 142.86. So balance with this. Okay, for C, so balance 142.86, 142.86, and then we continue with this. Okay, and this. So that is why I said we get reaction. Okay, we get reaction after we complete the member force. Okay, we get the reaction because this is roller, so roller must have vertical force. And again, here there is no value of horizontal force because this is roller. So I put zero here in order to prove that this one is zero. Okay, in order to prove AD is equal to 0. AD is equal to 0. So the last point that we need to check is A, joint A. Joint A. So what we have is we have 142.86. Okay, we get from C, so we get 200 here, and then this 142.86, this 142.86 must be. Okay, so this one is not 250. Okay, this one is not 250. That's the difference. Actually, that's the difference between 250 and 142.86. Okay, I forgot to calculate. It is 250 minus 142.86. Okay, this one because I copy and forget to change the value. Okay, this is 107.14. 107.14. So that at A, so A we have 250 here, 250. We have 250, and then this 250 we in upper side we have 142.86, and we have 107.14 to balance, okay, to balance joint A, and we have 200 here and 200 to balance as well, okay, to get balance as well. So this is how we calculate member forces in trust, in primary trust. Okay, we move to redundant trust. In redundant trust, when member force is redundant, we need to follow the following step in order to determine the member forces, because whenever member force is redundant, there will be no reaction because there are no external load. Okay, so what we need to do is we have to follow this step number one. We need to apply a unit value of FBD. We need to apply a unit value of FBD, and then using vector, we have to resolve in X and Y direction. Vector, we have to resolve in X and Y direction. Okay, vector. And then we need to balance the arrow. Balance the arrow means that if this is located at A, so this arrow must be balanced with opposite direction. Okay, must be balanced. This one also must be balanced at each joint, and then use trigonometry as well as interpolation to calculate horizontal and vertical member. Horizontal and vertical member. So this is how I interpolate. Okay, this is how I interpolate. So due to a unit value, so using this trigonometry, okay, we find this value and this value. Okay, so in the truss, so this is the truss. So actually, this is the value that we apply back, a unit value of redundant of FBD, and then this one we need to balance. Okay, again I forgot to draw this arrow. So we balance this as the first step. We balance this as the first step, and what we need to do, we have to we resolve this as first step, and then we need to balance. Okay, balance. Okay, balance, and complete this. Okay, this one balance with this. Okay, and then complete this, balance with this one, and then we move to A. We have, okay, this one balance with this, and then yang ni we balance with this, and there is no reaction value because reaction we calculate due to external loading, and in this case there is no external loading. So we analyze redundant system. Okay, using this step we have to number one, apply a unit value of redundant, and then using vector we have to resolve first in X and in Y, and then we have to balance the arrow. Okay, and after that we use trigonometry and interpolation to calculate horizontal and vertical. Means that from this we know that this one is horizontal value, this one is vertical value, so we put horizontal value here, okay, horizontal value and vertical value. So all these member forces we substitute, we put into the table. Okay, this is the table, and I have actually calculate all the value. So we have to have a column for N naught, N1, and this is actually come from the formula delta 1 naught means N1 N naught. This is F11. Okay, of course we need it. So this is delta 1 naught and F11. Then what we do, we substitute in into the compatibility equation, because we will determine redundant using compatibility equation. And then solve compatibility equation, we will get FBD. We will get FBD. So that is how we analyze this beam, this truss. This is how we analyze this truss. So the procedure is actually same. Okay, the procedure same. So we analyze, we solve redundant using compatibility equation. Okay, it means that we have to identify what is the redundant. Okay, identify using the solving this we will get negative delta to calculate FBD. Okay, what you should learn in trust analysis. Whenever okay, I will make a video for trust again, but having two redundant combination of reaction as well as internal force, member force as redundant. Okay, so till we meet again in the next video. Assalamualaikum warahmatullahi wabarakatuh.